Welcome. You are here because you work on vehicles that are becoming safer, greener, and increasingly autonomous. But you are also here because you know that with connectivity comes a new set of critical requirements. Every day we hear phrases like ISO SAE 21434 compliance, UN regulation number 155, or cybersecurity management systems. These are essential regulations for vehicle homologation. But if you are in the engineering department, the real question is, how do we comply at ECU level and how do we prove it? This asynchronous teaser course is about demystifying the how on ECU level verification and validation. Our goal is to take you inside the ECU, the fundamental building block for modern vehicles. Over the next few minutes, we will rapidly teaser 4 critical learning goals that will be elaborated in depth in the full course. First, understanding the change. How the change from legacy distributed to modern zonal architecture changes the rule of the game for verification and cybersecurity analysis. Second, mastering the protocols. A refresher on CAN, LIN, and FlexRay, but focusing on vulnerability perspectives. Why are they so easy to attack? Third, inside the ECU. We will break open a microcontroller and understand defense in depth. What are hardware security modules? What are cryptographic keys? And how does an HSM use them for services like secure boot or SecOC? And how to lock down communications. Fourth, practical verification. Crucial, in the full course we will move past the theory and go into practice. Here you will also get a little teaser on how we are going to do this. Welcome to the first part of this teaser module. To verify the security of a vehicle, we must first understand its skeleton, the EE architecture. This section introduces the evolution of vehicle EE architectures. On the left, we see a legacy network, a distributed model. It's a systems of systems nightmare. Isolated ECUs with complex and heavy wirings. Testing this was a nightmare of physical access. In the center, we have domain centralized architectures, where logical functions like powertrain or infotainment related functions share a domain network. It simplified some aspects, but it introduces also other bottlenecks and risks. Finally, on the right is the modern zonal architecture, the foundation of the software-defined vehicle. Now massive computing power is centralized in zonal gateways. They manage everything in their physical area. Notice also the large yellow box in the center of the car. That is the central high-performance computer. The core architecture components in all these architectures remains. It's the sensorics and actuatorics, the interfaces to the system and the physical world. The ECUs, specialized embedded systems for automotive applications, and often with hard real-time constraints. The general gateways, communication hubs, gateways, doorkeepers for security and isolation of separated sectors. For a cybersecurity engineer, it's important to verify and trust the gateways and the separations so that you can verify the communications they control within their given limits. In the next part of the course, we will look at the languages that these specific components use to talk to each other and across the different structures. We have seen the physical layout. Now let's examine the languages these embedded systems use. We call these automotive communication protocols, and they are the vehicle's nerve system. As a test engineer and also especially as a cybersecurity test engineer, you need to understand why different protocols are used. It's always a trade-off between speed, cost, reliability. First, we have the LIN bus. It's cheap and slow, used where speed doesn't really matter, like moving your seat or your mirror. Next, the working horse, CAN, and its successor CAN-FD, which allows a faster data transmission rate. CAN connects critical systems like engine and transmission. Critical for the implementation is also that CAN as such does implement zero native security. So we have to implement everything by ourselves. In native CAN, any node can speak to any other node. And then there is FlexRay. It's fast, deterministic, and expensive. It's used when you, for example, high performance cars brake pedal actuations. You need to exactly know when the signal will arrive and when the brake caliper will engage. FlexRay uses a fixed schedule to guarantee this. Here you see an overview and comparison of the different in-vehicle networks. See the different payloads, triggering events, and especially the security challenges these protocols pose. Your job in cybersecurity testing is not just to check if the data arrives, but to verify that the gateway is correctly filtering and routing these messages between the domains. Could an attacker send a LIN message that trick the gateway into sending a CAN message to the engine? That is what we are here to verify. Next, we will see how the locking of the protocol in the different defense layers is applied. We have looked at the vehicle network. Now let's set the focus inside a single ECU. A modern ECU must be like a vault. This is achieved through multi-layered approaches we call defense in depth. At the core of this approach is the root of trust. In automotive, this is the hardware security module, or HMS. The HMS is a physically distinct enclave inside the controller, separated from the main application CPU that runs the critical functions like engine control and braking. This physical separation is crucial. It means even if an attacker completely compromises the main application, they cannot easily steal the cryptographic keys stored inside the HMS key table. Those keys are used for the most critical security services. Secure Boot uses those keys to verify the signature of the application code before it runs. If the code is tampered, the mechanism prevents the ECU from starting. Secure Communication, or SecOC, adds a message authentication code, a dynamic digital signature, to messages on the CAN bus. The HMS on the receiving ECU can then verify that the message really came from the trusted source and wasn't spoofed. Your job in cybersecurity verification and validation is to design tests that confirm that these systems are not just present, but correct. You must prove that the HMS actually blocks incorrect keys, prevents unauthentic boots, and flags modified CAN messages. Next, we will see how we can do this with a hands-on example in our full training course. In the full course, we go into the depth of the complex architectures, the protocols, and the defense layers that a cybersecurity test engineer must verify. But here is the reality check. We will also apply this knowledge and make some hands-on experiments in our course. This is where the PENE framework comes into the picture. PENE stands for Pasta Emulator with no need of hardware ECUs. It's a powerful virtual verification environment that simulates the very components and communications we have discussed. And it's open source if you want to check it out. Penne runs entirely in a Linux or Docker environment. It provides you with a set of pre-configured virtual ECUs, such as a gateway, a body controller, or an engine controller. These software modules talk to each other using a standard Linux socket CAN interface, which mimics real CAN traffic. This is the course's V&V playground. Instead of connecting a physical debugger to a closed source ECU, we will use Python scripts or the Penne GUI to interact with the virtual networks. This allows you to perform vulnerability scanning across all domains instantly. More importantly, Penne excels at simulating cross-domain attacks. For example, you can write a test script that compromises the simulated gateway and then tries to inject unauthorized messages to the body ECU. In the full training course, you will master the Penne framework to design such test cases and prove that security defenses we discussed are actually working. In the next section, we will briefly show you exactly that. We have looked at the theory and the framework. If you want to see more, you can also check out this early video of the Penne framework's origin and in use. But now let's see the practical verification in action using the Penne environment. We are going to execute a fundamental message injection or spoofing attack. Imagine your target is a software-defined vehicle that does not have CySe enabled on the engine CAN bus. As cybersecurity test engineer, you must prove that this setup lacks or does not lack cybersecurity measures. We start our Penne core and deploy virtual gateway and virtual engine ECUs. In the central panel, you see the tool that we are using, a simple Python script. We use the Python CAN library to create a single valid CAN message, and let's say we set the RPM value to dangerous 8000 RPMs. In the script, we specify the CAN ID of the target, put our dangerous data in the payload, and hit send. On the right, we observe the result. The top terminal shows the constant CAN frame traffic from our virtual bus. A few frames later, you see our dangerous message frame has arrived. The question is, how does the engine ECU react? Since we have no authentication, the virtual engine ECU accepts the spoofed value as valid. If this were in a real car, the consequences could range from simple error lamp to unintended acceleration. In the full course, you will learn to write countermeasures, defenses that prevent these test cases from failing. Congratulations! You have taken the first step on the path to become a certified automotive cybersecurity verification and validation engineer or manager. In this brief teaser, we have covered the fundamental concepts of modern ECU architectures, the core communication protocols, and how to protect by using defense in depth. In our full course, we will elaborate those in greater details and with hands-on examples using the Penne framework. As mentioned, this is just the foundation. The road to true mastery comes by attending the full course. In our full course, we will go through 6 comprehensive units that take you far beyond these basics. You will master advanced cryptography, key management, go beyond CAN and LIN communication to high-speed automotive Ethernet, and learn the specifics of high-performance real-time computers in cars. And you will return to the Penne framework, but as practitioner. You will not longer execute simple scripts, but design and automate complex threat-based tests and evaluate the outcomes. This path is provided by the Cybertester project and takes you to the Euro SBI ASA certified automotive cybersecurity tester or manager certificate. Join our community of certified automotive experts and lead the change in green and autonomous mobility towards cybersecure automotive systems. Register for the full course today.